Good morning. My name is Dimitri Mankowski, and I'm a PhD student from Ruhr University Bochum. And today I will present you our paper, Waterfall, a capsule-based framework for evaluating traffic watermarking in anonymity systems. So first, let's say we have a client who connects to some server and wants to stay anonymous. And this client uses some anonymity system, for example, Tor, maybe also VPN. However, the issue is that metadata is observable, although the encryption hides the content, an observer can still see something like packet sizes, throughput, and the traffic rate, and thus link the client on the one side to the server on the other side. We can also use an active attacker. For example, on one side we can place an embedder, and the embedder embeds watermark by embedding some traffic pattern to the traffic. On the other side, there's a detector which attempts to detect this pattern. However, to evaluate these kinds of attacks, there are multiple challenges. First, the traffic can be really different. There can be bulk downloads, there can be also streaming, there can be voice calls, and all of these might require different traffic watermarks to survive the anonymity systems. In addition, protocols involved, there is buffering, congestion control, multipath routing, and various updates to anonymity systems such as Tor. And also often for prior work, assumptions stay hidden and they are evaluated in very narrow scenarios, for example, in idealized conditions. So what researchers and designers of anonymity systems really often need is a way to estimate the danger of watermarking attacks. And to build such systems like a framework, we first now have to look how to design watermarking attack and how the watermarking attack on encrypted traffic can look like. Let's say we have some traffic, so what can replace embedder the detector? And what can embedder do now? An embedder could drop some packets, reorder some packets, insert a delay, or maybe rewrite packets. For example, change the headers, like the CP headers, CP window. Then the traffic goes to an anonymity system like Tor, and on the other side, the detector sees some different changes to traffic pattern. Now the detector can measure the traffic, for example, seeing that there's a gap, that there's high traffic rate, or that there's low traffic rate. Also, embedder and detector have to exchange metadata very often. For example, this might be timestamps when the watermark is embedded. This might be also secrets, something like keys. And what we by looking at this, we identified three core semantics, namely the flow group semantics, which determines on which flows we are detecting the watermark, the coordination semantics, what is exchanged between embedded and detector, and the perturbation semantics, which defines how we modify, how we change the traffic. And by using this core semantics, we built Waterfall, which is an evaluation framework for watermarking experiments. And the central component of Waterfall is the capsule. And the capsule is a self-contained event-driven watermarking execution method. And it solves the three core semantics. It allows to select flows belonging to the watermark, to coordinate parameters between embedder and detector, and to act and observe traffic. The idea is that the capsule runs in the Waterfall runtime, and the Waterfall runtime can run multiple capsules and thus embed and detect multiple watermarks even at the same time. And so multiple watermark instances can be deployed on a connection to an empty system. Usually we deploy a Waterfall instance with an embedding capsule on the one side, and another one and with a detection capsule on the other side. And between the waterfall instances, parameters such as the coordination, the scheme, the key, the timing, the exchange, but also live measurements and also feedback from the detector. So Waterfall handles traffic matching the actions, monitoring of the traffic, measuring traffic, and also the communication, the Waterfall instances and the capsules. For evaluation, we evaluate 4 key questions, namely first, can we reproduce existing prior results? Then can we adapt watermarking schemes to live traffic and improve them? Can we adapt watermarking schemes and run them in new protocols such as for influx? And also can the same test bed implement and other defenses? And we focus our evaluation on 3 very different schemes, namely the flow rainbow and the extent-based tracing technique, which use drops, timing delays, also rate changes. So for our first research question for reproduction, we were able to reproduce 2 watermarking schemes. For the third one, however, we found a hidden assumption, and namely that the original rate watermark assumed that the flow control was the limiting factor. However, this is often not the case in modern networks, and instead the congestion control was the limiting factor very often. So what we did for the second research question, we tried to improve this watermarking scheme by measuring traffic. So in the fixed setting, we saw no rate changes and the signal was lost. However, when we measured throughput and delay and estimated the bandwidth delay product, we were able to choose an adaptive rate limit and restore the watermarking signal and improve the results for Rivian and also for core. For core, we were even further able to improve them in the third research question when we evaluated watermarking schemes on the Tor complex protocol, which splits one connection across 2 circuits or also lanes. And what we noticed is that when we embed watermark only on one circuit, it can fail because traffic is shifted to the other circuit. However, when we embedded a watermark in the merge traffic and detected both circuits, we gained higher performance, raising the detection rate from 65% previously to 88%, and this is due to the higher stability of the traffic. Also, the watermark becomes more stable. And finally, we showed the same aspect and also the defenses. So first, we look at the defense, whether we can detect the watermark, so non-flow attack, where we compared watermarked traffic with clean traffic reference, and we're able to flag all watermarked flows. Also, we made a difference to remove a watermark by delaying the packets and applying a constant pace, and thus we were able to suppress the timing signal. So attacks and defenses were able to use the same experiment harness. So the takeaways, with usable capsules, the watermarking schemes become comparable and adaptable. Live measurements reveal entry pair hidden assumptions, and watermarking attacks and defenses can be tested in the same framework. Thank you for your attention, and I would be happy to discuss any questions at the poster.